let's take a look at section 5.2, where we're going to look at linear systems of equations in 3 variables. So in our first system, we want to find the solution set. And if the system is dependent or inconsistent, we want to state that as well as give the solution set. And if the system is dependent, we want to express the solution in terms of the variable z. And sometimes that's not possible, but if it happens in this case, it is going to be possible. All right, so let's take a look at this problem. So I'm going to start off as my first step. I am going to eliminate y for the reason that that's actually the simplest thing for me to do. I'm going to use equation A, and I'm going to use equation B. And one reason this is an easy choice is because I'll only need to multiply equation A by 4. I won't need to make any changes to equation B. So the less I have to do, the better, because that eliminates the possibility of me making a mistake. So when I multiply equation A by 4, I get 16x minus 4y plus 8z equals 28. So every term of this equation is multiplied by 4. Equation B, I'm simply going to recopy, being very careful to copy the terms of that equation and to copy them correctly. And now I'm going to add 4 times equation A to B. And I get 21x. My y terms are eliminated since negative 4y plus 4y is 0, plus 3z equals 0. And I'm going to call this equation D, just so I have an easy way to refer to this should I use it again, and I will. My second step is to eliminate y again. This time, however, I have to use C. I must involve that third equation. I could either use B and C or A and C, but for the reasons stated earlier, it's easiest for me to use equation A, because since I'm eliminating y, and I'm actually choosing to eliminate y because there is a simple negative y term in equation A. I'm going to multiply equation A by 3, and that will give me a negative 3y in this new equation, and a positive 3y in equation C, which are going to result in the elimination of y. So I have 12x minus 3y plus 6z equals 21, plus 6x plus 3y plus 3z equals 24. So this is now going to give me 18x the y terms cancel out, plus 9z equals to 45. And I'm going to call this equation E. So I now will either eliminate, since I have 2 equations with the 2 variables x and z in it, I'm now going to eliminate either x or z. And I'm going to be, of course, using equations D and E to do that. So it's easiest if I can get away with just multiplying one equation by some multiplier. So I get minus 63x minus 9z equals 0, add it to E. So 3D is the equation I've written when I multiply every term of this equation by negative 3. And then I add that to E, which is 18x plus 9z equal to 45. And I'm going to add these together to get negative 45x. The z's, of course, cancel out, equals 45. So when I divide both sides of the equation by negative 45 in order to isolate x, I now find that x is equal to a negative 1. So now my fourth step, and I'm going to replace x with minus 1. So negative 21 times negative 1 gives me negative 21 plus 3z equals 0. So I have negative 21 plus 3z equals 0. If I add 21 to both sides, I wind up with 3z equals 21. And then when I divide both sides by 3, I wind up with z equal to 7. So I now have x, I have z, and of course I now need to find y. So my fifth step will be to use A, B, or C to find y. So 4 times minus 1 minus y plus 2z, so plus 2 times 7. So negative 4 minus y plus 14 equals 7. Negative 4 plus 14 is 10. 10 minus y equals 7. So I'm going to subtract 10 from both sides of this equation. Negative y is equal to negative 3. And now I'm going to multiply both sides of this by negative 1 to get y equals 3. So the solution set is the set that contains the ordered triple, negative 1, 3, 7. So there's one and only one point that all three equations have in common. And remember, each equation represents a plane. Our next system is shown. I'm going to focus my attention on the elimination of x. And to do that, I'm going to focus on equations A and B. I could have chosen just as well to eliminate y or to eliminate z, but I'm going to choose to eliminate x as my first step in this process. Now, what I want to point out is that whatever variable I decide that I'm going to eliminate, I focus on that variable and its coefficients in two of the equations. So since I'm going to eliminate x, I'm looking at 2x, and I'm focusing on A and B, equations A and B. I'm looking at that I have a 2x in one equation and negative 4x in the other. So if I multiply equation A by 2, I'll have 4x and negative 4x in the other equation, the opposites that I desire. So every term in equation 2 is going to get every term in equation A is going to get multiplied by 2. And it's really worth checking your work here at this whenever you're using a multiplier. Very easy to make a mistake. All right, and what I see has happened is that my two equations have not only added to cancel x, but I'm also canceling y and z, leaving only a 0 and nothing else on the left side. And moreover, 16 plus negative 16 also gives me a 0 on the right side. So all this allows me to conclude, since I've only used two of the three equations, is that the system might be dependent. That's all I know at this point. I won't know more until I bring in equation C. So I want to eliminate x again. Actually, I could eliminate any variable again since this caused the elimination of x. So I'm going to eliminate x again, but the general rule, since this work caused the elimination of all three variables, it doesn't matter what variable I eliminate next. But because I eliminated x the first time, I'm going to focus my attention on eliminating x the second time as well. So this time I see that I have a 2x in equation A and a 7x in equation C. So I have to use C. So I'm eliminate x and I must use equation C. So if I multiply equation A by 7 and equation C by negative 2, I will then have the elimination of my x term. And that's exactly what I want to happen. So I'm using equations A and C. I could have just as well used B and C, but I chose to use A and C. So 7 times equation A is 14x plus 28y minus 42z equals 56. And then negative 2 times equation C is negative 14x minus 28y plus 42z equals negative 40. So I wind up canceling all variable terms on the left side of the equation, getting only a 0. And when I add the two constants on the right side of the equals, I get 16. Now I know 0 doesn't equal 16. This is a false statement. Previously, the variables dropped out of the work I was doing and I got a true statement. That, because I had only used two of the three equations, allowed me to only say that the system might be dependent, which is not really a conclusion at all. But all I could say is it may be dependent. Now that I have eliminated all variables and wound up with a false equation, whenever that happens, even if I've only used two of the equations, I can immediately conclude that the system is inconsistent. This means that no matter what I do, I can't make all three of the equations true with the same three values of x, y, and z. So that means the solution set is the empty set. There are no solutions. So solution set is the empty set. So you can either write that as a set of empty braces, or you can write it as a 0 with a slash through it, but you don't combine the two. You use one or the other. Notice having all variables drop out and a false equation result trumps having all variables drop out and a true equation results. So whenever an equation with no variables that's false results, the system is inconsistent, even if you've only used two of the equations.